Hello, everyone, and welcome back to the GOCC this week. Today, we have Prairie Wentworth Nice speaking about Matroids, Polymatroids, and groups. But before I turn things over to Prairie, I just wanted to remind everyone that one, this talk is being recorded and will be posted to YouTube later, and two, of our community statement. So our community statement, just so we all remember, is one, we are all learning. Second, everyone has something to contribute. And finally, no one has all the answers. So if you have any questions, please go ahead, address them to the speaker directly, or if you prefer, put them into the chat and one of the organizers will make sure that they get asked. And without any further ado, Prairie, take it away.
Thanks, Mark. Yeah, so just to reiterate what Mark said, if you guys have questions, please interrupt me as we go. I will try to pause so that's easier. But definitely feel free to interrupt and let me know if there's anything in the chat I'm missing. I also want to check because I realized I didn't do this earlier, but if I like wiggle my cursor around, can you guys see it? Oh, fabulous. Okay. I'll try to minimize that, but it might happen some. Okay. So, right. So I'm going to be talking about Matroids, Polymatroids, and groups today and sort of go in that order. So we'll start with Matroids, and then we'll talk about Polymatroids and groups. And then at the end, we'll sort of connect back to Matroids and sort of what we've been doing with Polymatroids and groups, what that can tell us about Matroids in particular. And I should also say that a lot of this is joint work with my advisor, Ed Schwartz, here at Cornell. And here we go. So a little bit about Matroids, just some history for starting, is they were first introduced by this guy named Hassler-Whitney in 1935. He wrote a paper called On the Abstract Properties of Linear Dependence, where he actually sent out a lot of the sort of beginnings of Matroid theory. And Whitney did a lot of things in his career. He started off in graph theory, and then he had this paper in Matroid theory, and then he pretty quickly jumped over to topology for sort of the rest of his work. And then later in life, he got really interested in math education and started teaching math at the grade school level and talking about math education reforms. And that sort of surprised me. So I actually looked into that a little bit more because I was curious. And I found this article in the New York Times called Learning Math by Thinking. That's all about his views on math education. It's basically a lot of quotes of his thoughts and all about what he was thinking about. It's from 1968, and I pulled this one quote that I enjoyed. Dr. Hassler-Whitney, a distinguished mathematician at the Institute for Advanced Study in Princeton, says that for several decades, mathematics teaching has largely failed. He predicts that the current round of tougher standards and longer hours threatens to throw great numbers already with great math anxiety into severe crisis. And this quote just kind of entertained me because it's not unlike something we'd see now. Sort of a reminder that math education is sort of, people have a lot of the same views they used to and a lot of the same complaints. But obviously this is not a math education talk, so that's all I'm going to say about this. I just thought it was fun and wanted to share it. So we will jump into what was Whitney doing early in his career. So before Matroids, he was doing work in graph theory. And so sort of the reasoning for why he was doing stuff in Matroids came out of the types of things he was thinking about in graph theory. So in 1931, he has this paper with this great name that today is pretty useless called A Theorem on Graphs, which is not descriptive at all. But one of the things he's thinking about in this paper are circuits of graphs. And so these are it takes sets of edges and vertices where if you were to remove everything else and just focus on that subgraph, you'd get a cycle graph. So this sort of bolded triangle here would be a circuit, or the outside of this graph would form a circuit, or this other triangle here. And these are going to end up corresponding to minimally dependent sets when we look at graphs as having independent sets and get into Matroids in a bit. He also has a famous two-isomorphism theorem. He wrote this paper called Two Isomorphic Graphs. And this also is something that he was looking at graph two connectivity, which turns out to be related to Matroid connectivity. So this is also sort of a precursor to him thinking about Matroids. And then he was also looking at duality of graphs. So that's another one of his influences. And in particular, it was known that for an embedding of a planar graph, we could come up with a dual graph. And Whitney actually showed that if there is a dual graph of some graph, then the graph has to be planar. So he showed the converse of that statement. I don't remember which paper that was in. So that's sort of where Whitney's coming from. And we're going to talk about duality for matroids in a bit. So I wanted to remind you or tell you, in case you hadn't seen it before, what graph duality is. So if we have a graph like this one that has a planar embedding, we can find the dual of a graph by putting a vertex where every face of our graph is, including the outer face. So there's that vertex sort of in the top here. And then we draw lines between every edges of our original graph, connecting these vertices to make the edges of our dual graph. And some of the time, if we take the dual of the dual graph, we get back to the original graph. Though I think if you do stuff with embeddings, this might not always be true because you have to have the right embedding of your graph. But in this particular picture, you can just sort of go back and forth between the two graphs I drew. One of them is the dual of the other. Okay. So Whitney's thinking about all of this graph theory stuff, this duality, these circuits. And he's also looking at matrices, because obviously there are lots of matrices associated with graphs. And he made the following observation about column vectors of a matrix. He said that any subset of an independent set is independent. This should be a big revelation. This is, a standard fact in linear algebra. We should have covered this, hopefully. And then the other thing he observed, which is also something that we should remember from linear algebra, is that if I have two independent sets and one of them is bigger, I can take something from the bigger set and put it in the smaller set, and I'll stay independent. Right? My smaller set shouldn't span the bigger one if they're both independent. Is another way of thinking about that. And then he states in his paper, so this is from his paper in 1935, there are other theorems not deducible from these. And he means there are other theorems about the column vectors of a matrix that we can't get from just these two axioms. And he says, we give an example of a system satisfying these two theorems, but not representing any matrix. So we can give an example of other things that have this property besides matrices. And he says, let us call a system obeying A and B a matroid. And so this is his first definition of a matroid, which is the independent set definition of the matroid. And it's not the one that I want us to focus on today, but it's oftentimes, if you've heard anything about matroids, it's that they generalize linear independence. And this is what is meant by that statement. So this is where we're coming from. And when we're thinking about matroids, looking at the independent sets and the graphs can be really helpful. Okay, and I think that's been more than 2 minutes and we haven't gotten to the definition I want. So I met my promise of taking my time at the beginning. Okay, so this is the Matroid definition we do want. This is the rank definition of a Matroid. There's a gazillion other ones too, besides the two I'm showing you that we could use, but this is what I'm going for. So a Matroid is going to be a finite set of elements E, so that's key, finite sets here. And it's a function, which we call the rank function, from the power set of E to the integer. So it's integer valued and it has these three properties. The first property says that the rank of any subset can't be bigger than its cardinality. So if I'm looking at the rank of a single element, it can only be 1 or 0. If I'm looking at the rank of two elements, it can only be 2, 1, or 0, etc. And then the second property says that the rank of any subset Y has to be bigger than or equal to the rank of any smaller subset X. So bigger sets should have bigger rank or the same size, but they can't have smaller rank. And then the third property is a property called submodularity. It's written out here. It's a cool property. It's an important property, but we're not going to have to use this definition. So if you don't remember this inequality for the rest of the talk, that's okay. The key thing to just know is that we have a rank function. It has some properties, and we have this finite set of elements, and that's where we're working from. So let's look at an example, because examples are always nice. So this first example is going to be a nice little matroid. It's called U23. It's a uniform matroid. You don't have to remember that. It's a ground set. It has 3 elements, which I have very creatively, I think, labeled them 1, 2, and 3. And it has this rank function. So the rank of any subset of E is equal to the cardinality of that subset if there are less than or equal to 2 elements, and the rank is equal to 2 if there are more than 2 elements. And so what this looks like is the rank of any individual element, so the rank of 1, rank of 2, rank of 3, all equal to 1, rank of any pair of elements, Rank of 1, 2, 1, 3, 2, 3, all equal to 2, and the rank of everything is equal to 2. So this is a nice matroid. We could also, so connecting this back to graph theory, we could, instead of just viewing these this ground set E as just sort of random elements called 1, 2, and 3, we could also view these as edges of this cycle graph, 1, 2, and 3. And in general, for every graph, we can associate a matroid to it by looking at the edges of the graph. So if I take this other graph, which now has 5 edges, and I'm taking my ground set to be the edges of the graph G, the rank of any subset of my ground set is going to be the number of edges of a maximal forest in the subgraph induced by X. So what do I mean by this? For instance, if I look at 1, 2, and 3, that subset of my ground set, a maximal forest in this subgraph would only have 2 edges. It would just be a spanning tree in this case. And so the rank of 1, 2, 3 would be 2. Another way to think about this is whenever you have a cycle, that's always going to be a dependent set. Likewise, 1 and 5 is already a maximal forest. So this would also have rank 2 because there are 2 edges in that set. Okay, and so this is where our column vectors come in now. So we have matroids from graphs. We also want to look at when are matroids representable. So a matroid is representable over a field F if we can find these column vectors of some matrix, so that if we find a correspondence between our matroid elements and these vectors, the ranks of the space or the dimension of the space spanned by the corresponding vectors is equal to the rank in my ground set. So what does this look like? So for these 2 matroids, these are both representable matroids. I'm thinking about these matrices as being representable over the field F2 because it's small, it has 2 elements, and it's very easy to check. But the matrices I wrote will actually work for a lot of other fields as well. So if I look at the first matrix, if I look at any column, spans a space of dimension 1, every single element had rank 1. If I look at any pairs of columns, they span a space of dimension 2. If I look at all 3, still spanning a space of dimension 2. And then for my second example, this matroid has rank 3, the matroid from this graph. And so you need to start looking at, so if you look at the whole thing, it will have rank 3. You could check that. But if, for instance, we look at columns 1, 2, and 3, that corresponds to that top cycle in the graph, we see that indeed those 3 vectors themselves are just spanning a subspace of dimension 2, and that corresponds to the set having rank 2. So this is a representation for the graph.
A quick question.
Yeah.
For the representation for the graph, this isn't kind of the standard way to make a representation from a graphic matroid. Like, isn't it normally you take some kind of adjacency matrix so that you only have 4 rows?
Right. So normally you can assign directions however you want. Yeah. And then take an adjacency matrix of the directed graph.
Okay.
So,
but
yeah. And in general, like when you have a representable matrix or matroid, the representation is not unique. So that's like the standard way to do it, which is not how I did it here, for no good reason. But
sure.
Yeah.
Okay. Thank you.
But yeah, definitely could do it that way. And so this is the column view, and just to sort of reiterate what we did on the last slide was we looked at these first 3 columns of the matrix, and then we computed the dimension of the subspace spanned by them. And that's the same definition of representability I just had up on the slide. So then what you might remember also from sort of basic linear algebra is if you're trying to find out things like the dimension of the column space, this is equivalent to the dimension of the row space of a matrix, right? We can flip between row space, column space, and their dimensions, and they should all be the same. So we can also look at representable matroids from a more row space view. And it's slightly less common perhaps when you're first starting out, but it's going to be helpful for what we're doing later today. So we're going to say that a matroid on n, and I'm going to use n in brackets a lot, that just means the elements 1 through n, is representable over some field f if there's a subspace W of f to the n, where if I take a subset of n, the dimension over f of the projection of w onto sort of those coordinates is equal to the rank of S. And so what I mean by that is if I'm looking at this matrix below, right now, my space W is going to be the span of these row vectors. So 1, 0, 1, 0, 1, 0, 1, 1, 0, etc. Now, if I want to look at, say, what's the rank of 1, 2, 3 again, since we've done that one a lot, now I'm projecting these vectors onto just the first 3 coordinates. And so my new vector space representing just these 3 coordinates is going to be the span of this projection, 1, 0, 1, 0, 1, 1. And I guess you could add 0, 0, 0 in there, but it doesn't really add anything. So I didn't include it. So it's the same thing we just did. It's just a slightly different way of looking. And we should, if we check, sure enough, this span still has dimension 2. Everything should keep giving us the same number because I haven't picked any new subsets to look at. So we can make this observation. If W is a vector space over F, some finite field, then the number of vectors in W, F had better be finite right now because I'm going to take the cardinality of F and I raise it to the dimension of W. So you could check this, but we're just going to take this as a fact for the moment and say that this gives us another way to compute the rank. So the rank is our dimension of this projection space, and we can now compute this by taking the log base cardinality of F of W to the S. Now, is this a good idea? Probably not, because this involves listing out all of the elements in your vector space and counting them and then taking the log of that number. And like we have linear algebra and it can do this a lot better for us and a lot faster. So when you're working over representable matroids, like generally don't do this. It's not a good idea. But we're going to want to generalize this in a bit, and that's where it's going to be used. So that's where we're going with this. Okay. And this is where we're going to switch to duality in a second. So if there are questions about representable matroids, now's a good time. All right. So Metroid duality. So one of the things Whitney was looking at was graph duality, and Metroid sort of gave an answer to the question, if I have a graph that's not planar, what does its dual look like? Because for every graph, planar or not, we can associate a matroid. And it turns out we can always find a dual for a matroid. So for us, we're going to define the matroid dual to be this dual rank function. This is perhaps not the most intuitive way to define matroid duality. Another way to think about it is if I have a basis in my original matroid, the complements of bases become the bases of the dual. That's sort of the more intuitive, nicer way to think about it. But for our purposes, we're going to say that there is this dual rank function that you can write down, and it still gives you a matroid. It satisfies all the properties of matroids. And that's how we're going to build our dual matroids. And these will work nicely with graphs. So for graphs that do have a dual, you can take the matroid of the graph's dual, or you can take the matroid of the graph and then take the dual. And those will give you the same thing. So it doesn't matter where you take your duality. It plays nicely with graph duality. And then, as I mentioned, you can get a dual of any graph in this way. It always has a matroid dual. And then matroid duals also have this nice property, and this is true all the time, that if you take the dual of any matroid dual, you always get back to the original matroid. So very nice property. So one thing you might ask about is, how does this work with representable matroids, since we just talked about representable matroids for a long time? And it works very nicely. If M is a representable matroid, then its dual is also going to be representable. And not only is it also representable, it's actually fairly easy to write down a representation for the dual. So if we have a matrix representing M, and W is the row space of A, we can look at the orthogonal complement or the orthogonal subspace of W in Fn and write down a matrix representing that whose row space is that orthogonal complement. and that's going to give us the representation for the dual. So essentially, we can do some linear algebra and we can represent the dual. So here's one fast example. This is the matrix we were looking at before for the diamond graph. If we look at its row space, we can write down another matrix. I guess I didn't show you how I came up with this at all, but it does work. I promise that. I double checked that this is the orthogonal complement. This generates it, and so this matrix will generate or represents that dual graph that we saw very early on with like the green dots and the dotted lines. Actually, this is a matrix representation for that dual. Okay, so what have we done so far? So far, we've defined matroids to be a set and an integer valued rank function with some properties. We've said they're representable over fields via some subspace of the vector space Fn. We could compute the rank using this log thing, even though we probably shouldn't right now. And they have a nice notion of duality, and we can describe duality for representable matroids over orthogonal subspaces. So that's what we've done so far. And now we're going to jump over to polymatroids and sort of see what from this chart can we fill in with polymatroids. And this is also where our groups will come into play. Okay, so this is the definition of matroids we saw at the very beginning. So don't freak out, this is the same. This is the definition of subcardinal polymatroid, sort of, except I cheated and said, look at the above definition. So a subcardinal polymatroid is a finite set of elements E. It's a rank function that's real valued, which satisfies all of the same properties as matroids. So if you've seen polymatroids before, it's possible you've seen mostly discrete polymatroids or integral, also called integral polymatroids or integer polymatroids. Those are polymatroids that are your rank is integer valued, and you just satisfy properties 2 and 3 of matroids, but you get rid of the first property. So what I'm talking about are called subcardinal polymatroids, where I'm keeping intact all 3 properties of matroid rank functions, but now I'm letting my rank function be real valued. So that's the key difference here, is just what values our rank function is allowed to take. And I'm going to drop the word subcardinal for the rest of the talk, but I always mean subcardinal polymatroids. So what my advisor has done is he's constructed a new way to represent subcardinal polymatroids that's sort of analogous to the matroid story I just told you, but using finite groups. So instead of starting with a finite field, we're going to start with some finite group that I'm calling gamma. And we're going to take the direct product of gamma n times. So maybe we're going to start with Z3, and then we're going to look at Z3 cross Z3 cross Z3, which would just be this group 0, 0, 0, 0, 0, 1, etc. These would be the elements of our direct product. For any subset of our ground set, we can look at the projection of G onto sort of the coordinates associated with our subset. So we can just, if A is 1, 2, we'll just take the first 2 copies of gamma. If A is 1, 3, 5, we'll take copy 1, copy 3, and copy 5 of gamma. So we're just looking at some of the coordinates in our subgroup and projecting onto those coordinates. And so we're going to call HA is going to be the projection of a specific subgroup onto those coordinates. So H will always be a subgroup of my direct product group. And then HA is what happens when I project it onto the coordinates corresponding to A. And we're going to define a new rank function here. It's a real valued rank function, and it has this formula that's similar to the rank function for matroids that we looked at. So log base, now we're looking at cardinality of gamma, and it's of the cardinality of the projection of our subgroup onto the coordinates we're looking at. So this is why we were looking at this rank function before. So now we are going to have to list out elements, potentially. We can't use all of linear algebra anymore, so we'll have to make it work. So let's do an example. So this is a subgroup of the same group we were looking at on the last slide, Z3 cross Z3 cross Z3. And I've written up the rank function up above. So if I look at the projection onto just the first coordinate, the subgroup I get from that projection is the subgroup which contains 0, 1, and 2. That has 3 elements in it. So the rank of 1 is equal to log base 3 of 3, which is 1. If I look at the projection onto the last two columns, now the elements in my projection are 0, 0, 0, 1, 1, 1, 1, 2, etc. If you were to count them, there's 9 of them. And so the rank here is log base 3 of 9, which is 2. And if we look at the entire subgroup, it also has 9 elements. So that tells us that the rank of the entire Polymetroid is also 2. And we could go through and do this for all of the subsets. I've done that for you for this group. Rank of any individual element will be 1, rank of all the pairs is 2, and the rank of the entire thing is 2, we just saw. So this particular subgroup I happen to choose is it gives us a group representation of U23. And you might say, but Prairie, Z3 is also kind of a field, like it's kind of the same as F3, like it's the abelian group of F3. Yeah, so this is actually kind of the same as a vector space representation if we were to view this as a field instead of a group. So this example, I haven't actually done anything super new. But it is to demonstrate that this does work with Metroid representability. It corresponds nicely to what we saw before. And so let's look at an example where we have something that's most definitely not a field, and this is looking at Z6. So I've put up a new subgroup. I've put up our rank function again as a reminder, and I will now give you all 60 seconds to a minute or so to compute some ranks on your own and then see if they match what I got. See if you've been following along. Okay, give me like a thumbs up if you've computed something. Okay, I got a couple thumbs up. It's okay if you didn't finish and give you enough time. Okay. Okay, so where are we at? So if we look at the rank of individual elements here, so the rank of the first column, you should have gotten 1. There are 6 elements here, from log base 6 of 6. But now we get some things that are not integers anymore. So the rank of the, if we project onto the second column, we have only 3 elements. So our rank is log base 6 of 3. And if I look at the last coordinate, then my rank is log base 6 of 2. So here's where we start to see things that are not only integers, they're also not rational. So this is why it's important for us to have a real valued function. And we can also check the rest of the ranks. And so this is an example where even like the entire Polymetroid itself doesn't have an integer rank. So there's lots of possibilities for what these ranks could be. Although if you fix the group, there's sort of like a smaller subset of possible rank functions you could get. So that's kind of nice. Like for Z6, you should always get things that look like log base 6 of 2, log base 6 of 3, 1, and like combinations of those added together. You shouldn't get log base 6 of 5, for instance. Okay, so it's not immediately obvious, but we can show that this rank we've defined, it is a subcardinal polymatroid. It meets the 3 properties of the rank function that we are required to have. The first 2 are fairly straightforward. The third one's like a little bit more work, but also not too bad. And we're going to say that if gamma is a group, a polymatroid R is representable over the group gamma if there's some subgroup H of gamma to the n where we can define the rank function of H, and it gives us the same rank function we had before. So if we have a group, we'll call it representable. Okay, so what about Polymetric Duality? We're going to define duality the same way I defined it for matroids. So we're just going to say you're a dual if you have this rank function R star instead of that's based on your rank function R. And this is, I'm using the same exact definition for R star as for matroids. I'm not changing anything. And again, we could show that this will still be a subcardinal polymatroid. It'll still meet all of our properties. And in this case, so with matroids, you can talk about dual in terms of bases and independent sets. We don't actually have a good notion of independent sets for subcardinal polymatroids. So this is actually our definition of dual. Like there isn't a nicer, better, more intuitive one. This is what we're taking to be the definition.
And just a quick question. Here, subcardinal is really important, right? Like
Yes.
This definition doesn't really make sense for non.
Right. Yeah. So if you look at, if you think about integer polymatroids and or K polymatroids where the rank of an individual element has to be less than or equal to some integer like 5 or something, then you need to multiply where the cardinality of S is. You need to multiply that by 5 or by K, whatever your K is. So there is a way to do Polymetroid duality for other types of polymatroids, but yeah, for this specific definition, yes. Otherwise, I'll start getting negative numbers, which doesn't make sense for my rank. So yeah, it's a good question. And so like Metroid duality, Polymetroid duality has the nice property that if I take the dual of a polymatroid and then I take the dual again, I get back to where I was. And sort of like Metroid duality, there is a representation for the dual. However, in this case, it's not always going to be a representation by the group itself. I decided I didn't want to spend the whole talk talking about what this is, so I'm going to give you the one bullet version of what this is. And that is, we can describe a representation for the dual of the polymatroid, which is, it'll be represented by the irreducible representations of the induced trivial representation of H and G. If that doesn't mean anything to you, that's okay. We're not going to use it further. But just know that you can do some representation theory and we can get a nice dual. And there is some really cool stuff that comes with this. But I'm just not going to focus on it right now. And this fills in sort of the rest of our chart. So polymatroids defined the same as matroids, except our rank is real valued. Instead of being representable over fields, we're representable over groups by subgroups. We have sort of a similar way of defining rank, where now we're looking at the cardinality of the group and the cardinality of projections of the subgroup. And then there's some notion of a dual and duality for representable polymatroids using some representations and stuff that I'm not telling you about. And I also wanted to mention while we are on this slide that if you came to last week's talk, there are also some connections to what Ben talked about last week. So if you weren't here, take the next minute to put in your schedule to watch the talk because it was fun while I talk about this, because this might not make sense. But if you were here, which several people were, so some things Ben mentioned last week were characteristic polynomial. So for matroids, this is like, it's a polynomial in lambda, I should say. And we're taking the sum over all the subsets of -1 to the cardinality of our subset, lambda, and then this thing with ranks. You can define the same thing for polymatroids, but you might notice something if you look carefully at this formula, and in particular, if you look at like these rank things down here, these are not integers anymore. So your characteristic polynomial is not actually a polynomial in many cases. That being said, it's still a useful thing to define. It's just maybe not as nice to call it a polynomial because it's not. So one version of Crepo-Rota's critical problem is that we can, so chi of lambda is what we usually call the characteristic polynomial, and I didn't write it on the first line here because I ran out of space on the slide. But if we plug in the cardinality of F, if we have a representable matroid over F, and we plug in the size of F, into our characteristic polynomial, this can tell you the number of vectors in the vector space representation with no coordinate equal to 0. And you do get something similar on the polymatroid side. If you take this characteristic polynomial that's not a polynomial, and you plug in the size of the group, if it's representable, you still get an integer, which is kind of miraculous. And it gives you the number of elements of H with no coordinate equal to the identity. So it gives you something similar. And if you look at other versions of the Crepo-Rota critical problem, where you're looking at like the size of your field to the K or something, you can get a corresponding thing on the Polymatroid side as well. So that's pretty nice. So that's sort of a connection to some of what Ben talked about last week. We can do that too. Okay. So then something we can do in both Polymatroid world and Matroid world that works pretty much the same is we can look at minors. So we can look at smaller pieces of our Matroids or Polymatroids. So we say that something's a minor of another Polymatroid or Matroid if we can get it by a series of deletions and contractions. So these are two operations we're allowed to perform on Matroids. Deletion is pretty easy to think about, just sort of get rid of some of the things in your original set and everything else stays the same. And contraction is a little bit more complicated to think about it. You could think about it as a dual operation of deletion. You could think about it in other ways. I'm not going to go into what it is, but essentially you can make some smaller Matroids that live inside your bigger Matroids, similar to what you might do in graph theory if you're looking at minors of a graph. And it's a very nice theorem in Matroid representability that holds also for our Polymatroid representability, that if you have a Matroid or a Polymatroid representable over some group, then every minor of that Polymatroid or Matroid is also representable over that group or field if you're looking at representability over fields. So that's very nice. If something's representable, all of its like small pieces also are. And this brings us to sort of excluded minor theorems are types of theorems people look at in both graph theory and Matroid theory to sort of classify what might be representable by what or what has some property. So a Matroid R is going to be an excluded minor for the class of Matroids represented by a group gamma if it's a minimal Matroid not representable by gamma. So if R is not representable by gamma, but all of its minors are. So it's like the smallest thing that can't be represented, essentially. So there are a number of excluded minor theorems for representable Matroids. Starting all the way back in 1958, Tutt found that U24, which is similar to U23, the Matroid I showed you sort of at the beginning, is the unique excluded minor for the class of binary Matroids, so Matroids representable over F2. And there was actually a conjecture by Rhoda in 1971 that there's a finite list of excluded minors for the class of Matroids representable by any finite field F. A few years after that, Seymour and Bixley in 1979 found a complete list of excluded minors for ternary Matroids over F3. And then in 2000, Gielan, Gerards, and Kapoor found a complete list of excluded minors for Matroids over F4. And that's kind of it. That's except that in 2014, I believe, Gielan, Gerards, and Whittle announced that they have a proof of Rhoda's conjecture, that there's a finite list. And then they said it would take a long time to write up, and it's taking them a long time to write it up, so they were correct. But it also doesn't, the way their proof, the tools they use in their proof doesn't actually give you the list of excluded minors or tell you how big it might be. It doesn't bound it in any way. So they found that there is a finite list, but nothing about what that finite list looks like. So things like, what about F5? Still open, still unknown. So there's like a lot here, but also it's really hard. You'll notice there's a big jump from F3 to F4. There's like 21 years in between, and it sort of just gets harder as you get bigger. So that's some of the work people have done for representable Matroids. And so we wanted to look at what about representable Polymatroids now over groups. But to make it a little bit easier, started with Matroids, because thinking about Matroids is easier than thinking about all subcardinal Polymatroids. And sort of the first thing we looked at was actually non-abelian groups, just because they're sort of the most different. And it was sort of like, what's there? Like, is this kind of interesting? And this turned out to be a case that we could classify entirely. So U23 is the unique excluded minor for Matroids represented by non-abelian groups. So if a Matroid has U23 as a minor, and this is any Matroid with a circuit of size 3 or bigger, it's most Matroids have U23 as a minor, it's not going to be representable by any non-abelian group. If it doesn't have U23 as a minor, it's representable by all non-abelian groups. And in fact, U23 is also representable by all non-abelian groups. And so in this particular instance, we can completely classify Matroids that are representable by non-abelian groups or not.
A quick question.
Mm-hmm.
Is this only Matroids or what about
Yes.
Polymatroids? Okay.
Yeah, this is just Matroids. Yeah. You can certainly represent other Polymatroids by non-abelian groups. Just take your favorite non-abelian group, take some direct products, write down a subgroup, and you've got some Polymatroid. But if you've picked something that's like not, where sort of not all of the columns are independent, like if you've picked a sort of interesting subgroup that's not just the direct product of the group itself or something, then you won't have a Matroid, is one way you could think about it. So this is just Matroids. So after this, another thing to look at was, okay, well, what about Matroids in abelian groups? Can we come up with something similar? And this turns out to be not as nice and simple in terms of one statement. So one thing we did find is that if you have a Matroid representable over Z mod KZ for some K, and you have M, an integer dividing K, then your Matroid is also going to be representable over Z mod MZ. So something like, if you know that you're representable over Z mod 4Z, you're also going to be representable over Z mod 2Z. And that's nice to some extent because we know about all of the Matroids representable over Z mod 2Z. So we know if you're not representable by Z mod 2Z, you have no chance of being representable over Z mod 4Z. But it doesn't tell us about the other way. So like, what about the converse? Since we know all of these Matroids over Z mod 2Z, can we say, okay, and they're also representable over Z mod 4Z and sort of like be done? And the answer to that is we can't go the other way. And our counterexample to that is the Phanomatroid. So on the left is the Phano plane picture. Don't worry about why it looks like that, but it's pretty, so I put it there. And Whitney showed actually in his very original paper that the Phanomatroid is representable over a field F if and only if F has characteristic 2. So for our purposes, it's representable over Z mod 2Z. That's what we care about. And what we showed is that this is not representable over Z mod 4Z, and we were able to do that in a very similar proof to Whitney's original proof. His ideas kind of extended over to what we were doing. So this is our counterexample. So we can't get, so if we're looking at Z mod 4Z, we can't get all Matroids representable by Z mod 2Z. So another class of Matroids to look at are regular Matroids. So regular Matroids are representable over every field. They're very nice Matroids. For instance, all graphs are regular, all graphic Matroids. And there are only a few excluded minors for the class of regular Matroids, so it's not as many to check. And what we found is that regular Matroids are representable by all cyclic groups. And in the case of Z mod 4Z in particular, that Matroids representable over Z mod 4Z is exactly the class of regular Matroids. So we're able to classify all Matroids representable by Z mod 4Z. So this is sort of where our excluded minor results are at the moment. Done some other work as well. So I haven't talked about the dual. I've avoided talking about the group dual here, but it has some really interesting implications for coding theory. So I've also found a Green's theorem for the dual of a group code and a McWilliams identity for non-abelian groups, which has been an open question in coding theory for a while, and we were able to describe this. So that's sort of another area that I've been working in related to this. And there's so much we can do in the future. So there's a lot of excluded minor questions that still exist, some of which might even be like fairly tractable. Like what about polymatroids over Z mod 4Z or matroids over other abelian groups, or what Mark asked earlier, what about polymatroids over non-abelian groups? I haven't even thought about that one at all, really. I've sort of stuck to abelian groups recently. There are other questions in coding theory to look at. We talked about the characteristic polynomial a little bit. Another question might be like, is there a reasonable analog of the cut polynomial? What sorts of information can you get from that? And basically, there's just a lot of Matroid theory that you could say, how does this work in our setting? There's a lot known about representable Matroids. They're sort of the nicest class of Matroids. They're the ones people study. So what can we sort of bring over from Matroid theory into this new realm of representable Matroids? Thank you all very much for coming. I'm going to end there.
So thank Prairie. Do we have any questions for Prairie? Okay, I have first question, which is, so you got Matroids representable over Zmod 4Z are all, well, are if and only if it's regular, so
Mhm.
representative over all fields. And you said that that was true for any cyclic.
One direction of that is true. So
Right.
if you're regular, you're going to be representable over any cyclic group.
Does
But
that
the
get you
other groups aren't gonna.
all cyclic groups whose order is divisible by 4? Because if you aren't representable over Zmod 4Z, you aren't representable over
Yeah.
Zmod 4M.
I think yes, that seems likely.
Okay.
Yeah. I hadn't thought about that, but yeah, that should follow. Yeah.
Okay, well, that's a quarter of the integers down.
Yeah.
Other questions for Prairie? Okay, let's thank our speaker again.